you have a function of multiple variables and you're trying to find the absolute maximum or the absolute minimum, you need to check any critical points on the interior of the region, you need to check the boundary of the region, and you need to check the boundary of the boundary. This theorem is called the extreme value theorem, and it is often credited to this guy, Karl Weierstrass. Karl Weierstrass, that's the German letter, they have a double letter S. I think it's called a Esset. I can't draw it. I don't know. Karl Weierstrass. And the point is that if you have a function that is continuous and it's differentiable all except for a few places, then it must obtain its maximum value, and that maximum value must either be at one of the boundary points or at one of the critical points. So I've drawn an example here, and this point right here, that's the highest place that the function ever goes. So that's the absolute maximum, and you can see it kind of happens at one of those little cusps. So that's a place where the function is not differentiable. Then there is a local minimum right here and a local maximum right there. But the absolute minimum, the smallest that the function ever gets in this example, is at this endpoint right here. So in Calc 1, what you needed to check was any points on the interior of the region or on at the boundaries. One thing that I want to mention about this is this assumption right here. This is really a very strong assumption to assume that the domain of the function is a closed and bounded region. If you're interested in math and you study math more, you'll learn more about what a powerful assumption it is. And generally, we have a notion that is a kind of way to generalize this idea of being closed and bounded, and we call it compact. So, you know, if you're learning about this for the first time, know that this idea of closed and bounded is a really important thing, and it does come up more later in the theory of math. Now that we're in Calc 3, when you bump the dimension of the domain up, it makes the process just a little bit more complicated. So here I've done my best to draw a part of a surface, and we're only considering some this little triangle in the XY plane. Those are all the inputs that we care about for this problem. And so, you know, I've tried to draw it so that there's like a little local maximum, maybe right there above the boundary, and then maybe this absolute maximum happens right over there, and then maybe the absolute minimum, oh, I didn't line it up very well. I don't know, maybe the absolute minimum happens right there. You know, this drawing isn't perfect, but the idea that I'm trying to communicate is that now when you look at the domain in this problem, you're going to get some kind of triangle in the XY plane. So let's look at it. Let's suppose that it looks something like this. So now we're going to need to check the interior. That's all the places on the inside of the region. Also, we're going to need to check the boundaries just like we did before. And back in Calc 1, the boundaries were just those two endpoints. So now we have three boundaries. We have this boundary over here and that boundary over there and that boundary over there. So if we just say, for example, look at this, like this is a triangle and there's kind of a hypotenuse that is the boundary, then that boundary itself is a line. And so just like before, when we had the piece of the domain that was a line, we had to check the endpoints of that line. So we also need to check those two endpoints as well. I call those the boundary of the boundary. So it's kind of fun to imagine. This is all we ever do. That's as deep down this rabbit hole as we ever go. But I guess if you started pushing things into higher and higher dimensions, you'd have to check the interior of the region. You'd have to check the boundary. You'd have to check the boundary of the boundary, and then maybe then you would get a line, and so you'd have to check the boundary of the boundary's boundary, you know, and if you were in like 37 dimensions, you'd have to check the boundary of the boundaries. I mean, we don't go that crazy with it. All we ever do is domains that are regions in the XY plane. But let me try to just sort of put this in a method. the method that you used, find absolute extrema. If you're looking for extreme values, what you need to do is check the critical points that are on the interior, check the boundary. In that case, in this example that I've done here, there's going to be 3 boundaries, right? These 3 lines. And then you're also going to need to check any corners of the boundary, any places where the boundary is not differentiable. In this example, that would be these 3 red dots here. So you check you check the interior, you check the boundary, and you check the boundary of the boundary. Here's a pretty classic example. I think it's going to be pretty straightforward. We have some kind of paraboloid here, and we're asked to find the absolute extrema. And then they give us this region that's bounded by these curves. X equals 0, that's this line right here, the y-axis. Y equals 2, that's this one up here. And then y equals 2x, that's this line right here. So our region is a closed and bounded region in the xy plane. And so I'm going to go through this method for checking for critical points that are on the interior, and then we're going to check these boundaries, and then the boundaries of the boundaries. But right off the bat, we can actually just read off what these corners are from this setup here. This is going to be 0, 0 is going to be the bottom corner there. And then up here, this is where y is equal to 2 and x is equal to 0. And then this corner right here happens when y equals 2 and y equals 2x. So that means this point must be 1, 2. So I've already got some critical points to include in my list here. All of these, because they are the boundary of the boundaries. I guess I'm kind of doing it out of order, I guess, now that I think about it. I sort of always do step 3 first, but it doesn't really matter the order that you do it in. So for these interior critical points, they're just the same as for the local maximum or minimum. This is either where the gradient is equal to the 0 vector or where the gradient would be undefined. So let's look for those first. Okay, so I just took the gradient and set that equal to the 0 vector. So, I mean, that's a complicated way of saying you take the x partial derivative and set it equal to 0 and the y partial derivative and set it equal to 0. And this was just like a polynomial, so it's pretty straightforward. And then, this happens a lot of times in these like academic examples when textbooks try to cook up problems where the numbers all play out in a nice way. You often end up with duplicate critical points, and that's okay. Here again, we already had this critical point 1, 2 because it was a corner of our domain, and then when we started looking for the critical points, we got it again. It doesn't have to be the same. This time it just kind of worked out that way, just a coincidence. Okay, so now that I've checked the any critical points that could happen on the interior of the region, I'm going to go start checking for any critical points that are on the boundary of the region. So I have 3 boundaries because this region is a triangle, so I'm just going to name them A, B, and C. So boundary A is defined by the equation y is equal to 2. So right now, for this part of the process, all I care about is the value of the function on this line right there, the line y is equal to 2. So this is kind of cool because what it does is it reduces the problem from being a function of multiple variables to just being a function of a single variable, because now y is fixed, y is just 2. So now I don't have f of x, y, I just have f of x comma 2. So I can go in and put a 2 in for all these y values. And then, I've covered myself up. And then what I'm going to do is I'm just going to, treat this like a Calc 1 problem because now it is. I mean, this is now just a function of one variable. So I'm just going to go through all the Calc 3 processes of finding any critical points on this boundary where y is equal to 2. Okay, and this coincidence continues here again. So when I plug in y equals 2, I get this function that is now just a function of x alone. And then, in Calc 1, the way that you maximize the function is you look for places where the derivative is equal to 0. So that's what I did. I just took the derivative and I set it equal to 0, and that gave me x is equal to 1. And so then I just combine them together. So x is equal to 1 and y is equal to 2 again gives me the critical point 1, 2. So this critical point keeps showing up. That doesn't really mean anything. It doesn't mean that it's more likely than any of the other ones to be a maximum. It's just, kind of part of this process. A lot of times you just end up with a bunch of repeat points. So we really need to check to see whether or not the point 1, 2 is an extreme value. Okay, so it happened again. Now I am checking the boundary B. That's this sort of left side of the triangle there. So that's where x is equal to 0. So I just plugged x equals 0 into the function. That gave me a function of a single variable. And then I'm just rolling through the whole Calc 1 process where you just take the derivative and set that equal to 0, and that gave me y is equal to 2. So then if x is 0 and y is equal to 2, I produce that critical point right there, 0, 2, which was already part of our list. And that's okay. It doesn't have to happen this way. It is happening this way. And they do a lot of times in these academic examples, but it really is just a coincidence. It doesn't have to happen like this. Okay, so the boundary C is actually the most interesting boundary in this problem. So if y is equal to 2x, that's this right side boundary right there. What we're going to need to do is substitute y equals 2x into the original function. So that's what I've done. I've just taken all of these y values throughout the function, and I've just replaced them with 2x, okay? And then I just simplified that, and that gave me this function of x alone. And, then it's just Calc 1 business. You just take the derivative and you set it equal to 0. And guess what I got? X is equal to 1. So then if x is equal to 1 and y is equal to 2x, then y is equal to 2 times x, which is 1. So again, we get this point 1, 2. So it's a bit of a fluke, but whatever, math happens that way sometimes. So in this problem, we just ended up with 3 critical points. So now we know for sure the function must have its maximum value and its minimum value at one of these 3 critical points. So all that's left for us to do is just plug them in and see which one's the biggest and the smallest. So let me do that. Okay, so that's it. Now all you do is you just take all the critical points that you have found from those previous spots, and you literally just plug them in, and then you just pick the biggest and the smallest. So the biggest point happens here at 0, 0. So the local maximum is 1. And the smallest point happens here when xy is 1, 2. So the local minimum is -5. So, this is really like actually kind of an algebra problem hidden in a calculus class. Most of the difficulty that students have navigating these is actually just plugging in the boundary points, like whatever these equations of the boundaries are, and then, managing taking the derivatives and solving those equations. So, there isn't really much else to say about the theory. Kind of the next step for you should be to just sort of get in there and get your hands dirty with the actual problems that you have to work with. Don't hesitate to let me know if you come across a tricky one or you get stuck on something.